First of all, the name of this chapter, if you look, chapter 2 is the chapter we're doing, and that starts on page 10. So if you'll turn to page 10, please. Linear motion. So that's what we're going to talk about. Things that are moving in a line. So that's one dimension. So if I move along a roadway, I can either go east or west. The road is straight, okay? I can either go east or west. Or if I throw something straight up into the air, it either goes up or down, right? So that's what we mean by linear motion, one-dimensional motion. Later, when we talk about things moving like this, right, that thing as it flew through the air, it moved both horizontally and vertically. So that's two-dimensional motion. And if I fly a plane like this, you know, it's going this way, that in 3 dimensions, right? So that's three-dimensional motion. So this year we're going to start off talking about one-dimensional motion, which is also called linear motion. And then we're going to go into two-dimensional motion, and that's it. Okay, we're going to limit ourselves to 2 dimensions. Although, of course, we live in a 3-dimensional world, but we don't do too much or very much at all talking about 3-dimensional. If you want to get into 3-dimensional, you can take AP Physics next year, and we do some stuff in 3 dimensions. But here we go. Let's start off. First, you have to realize motion is relative. What does that mean? It means whenever you are moving, you have to have someone from your family with you. No, not that kind of relative. Noah, what do you think? Motion is relative. Can you think of a synonym maybe for relative in this context? Exactly. That's exactly what I was thinking of. In comparison to, compared to some reference point. So normally if we say, hey, that car is driving 55 miles per hour, we don't say it. That car is driving 55 miles per hour compared to the ground. But that's what we mean, isn't it? Right? Right now, how fast are you moving? 0 miles per hour, right? You're at rest, we say. And we didn't say it compared to the ground. But what if I ask, how fast are we moving compared to the sun? Holy cow. You know, that Earth is going around the sun in its orbit. If you measured that distance, which is a big distance, and divided it by the amount of time it took, 1 year, and you converted years to seconds, and you took the number of miles, and you divided it by the number of seconds it takes to go around the sun, guess how fast we're moving? There it is right there. 18 miles per second. Really? Yes. How come our hair isn't flying back and our skin pulling back and we're 18 miles a second? How come? Does your hair fly back when you ride in your car at 65 miles per hour? Not with the windows closed, right? That's because everything in the car is moving at 65 miles an hour with you. The air, the person sitting next to you. So everything in the car seems to be at rest compared to you, even though you're moving 65 miles an hour compared to the road. You ever been sitting in a train and you're like, come on, train, let's go. I want to get going. And you look out the window and you say, oh, we're moving. And then you realize, oh, no, it's the train next to us is moving. Never happened? One time, I was in my car, and I'm pulling into 7-Eleven. And I pull into the parking space, and I look next to me, and there's a car parked in a parking space next to me. And so I'm watching that car as I put on the brake, and I use that car to judge how fast I'm going, right? And I start to slow down, and I can tell by the motion of the car that I'm slowing down. But then I expect to stop, and I'm pushing on the brake harder and harder and harder, and I'm not stopping, or so I thought. What happened was I pulled in this parking spot, and as soon as I pulled in the parking spot, they started backing out of the parking spot, and I didn't know that. And so I was stopped, but I thought I was moving because the car next to me was going that way. Right? When you pull in the parking space and you just look at that car, that's the relative motion between you and the car next to you. So like this, it looks to me like this car is moving backwards, and then I stopped, and it actually did start moving backwards, but I thought it was at rest, so I thought I was moving forward. And I was pushing on the brake going, oh my gosh, my brakes don't work, just for a second. And then I realized, oh, they're moving backwards. So motion is relative. That's what, okay. All right, now how do we measure motion? How fast is something going, right? We call that speed, of course. What is the speed of your car, right? And it is the rate at which distance is covered. So that, let me scroll down here. That is an important word, rate. Rate has a specific meaning. The rate something happens means we're comparing to time, okay? So how much, I say I went 20 miles. Okay, but how much time did it take you? Now, if it took me 1 hour, you say, oh, my speed was 20 miles per hour on average for that trip. But if it took me 30 minutes, now my speed is 40 miles per hour, right? Yeah, I go faster. I get there quicker. I cover more ground in less time. So we call that rate. So when you notice at the units of my speed, miles per hour, or meters per second, or revolutions per minute, those are all different measures of speed, but they have one thing in common. They're all some distance divided by some time. So if you want to talk about your car, miles per hour is a good thing to talk about. Talk about continental drift and how fast is the North American plate moving away from the Eurasian plate. Miles per hour would be a silly unit to use. Centimeters per year would be more, or how fast do your fingers grow, right? In miles per hour. No, that's not a very good unit to use, right? Centimeters per day, maybe, or centimeters per month. You say in 1 month, my nails grew 1 centimeter. So my nails grow at, on average, 1 centimeter per month. That's a legitimate unit of speed, right? A distance divided by a time. Okay. Instantaneous speed and average speed, there is a difference, okay? When we talk about instantaneous speed, it's kind of nice. The word is right in the definition is right in the word instant. What is your speed at any instant? So when you're in your car and you look down at your speedometer, it tells you how fast you're going at that moment. That's your instantaneous speed. Or if a policeman is hiding behind a building and he gets you with the radar gun, that tells you how fast you're going at that instant. That's your instantaneous speed. Whereas your average speed, let's say we get into our car in the parking lot right here in Lynbrook High School, and we drive to Santa Cruz. I looked it up. From Lynbrook to Santa Cruz is 29.12 miles. And I look at my watch, I say, okay, let's go. We drive to Santa Cruz. We get there. I look at my watch again, and it took us 37 minutes to get there. So I take my distance, and I divide it by my time. 29.12 miles divided by 37 minutes comes out to 0.787 miles per minute. Now, who speaks in miles per minute? Nobody. So I'm going to do a conversion. And this will be something you'll do later in this unit yourself on your homework. If I want to convert miles per minute to something that's more common that I'm used to, miles per hour, I can multiply. If you took chemistry, you're aware of unit conversion. This is what we call a unit conversion. I want to convert miles per minute to miles per hour. So this will, whenever you multiply something by the number 1, it doesn't change, right? It stays the same. So, and what equals the number 1? Any fraction where the numerator is the same as the denominator is the number 1, isn't it? So I can take the units that I want to get rid of, which is miles per minute. I want to get rid of minutes, and I want to replace it with hour, so to make it miles per hour. So I know if I put minutes in the numerator, it'll cross off or cancel out with this minutes in the denominator. And that will make the minutes go away. And then I'm going to put the hour in the denominator so it'll be left over, and I'll end up with miles per hour. And to make this be equal to 1, I say how many minutes are in an hour. And 60 minutes are in an hour. Now that's the number 1, but the only thing that's going to change now is my units and the value of, so when I multiply 0.787 times 60, I get 47.22. The minutes cancel off, and my units, I'm left with miles per hour. Okay? So that's an introduction to a unit conversion. You'll get more practice with that later. Okay, so 47.22 miles per hour, that's my average speed from here to Santa Cruz. Did I drive 47 miles per hour on Johnson Avenue? You better not, right? The speed limit is 35, as reminded by that flashing sign that says you're going over 30 miles an hour, even though the speed limit is 35, but we're going to flash it in your face because we live in Cupertino. There, thank you. Somebody laughed. Okay. Did I drive 47 miles on 280? No, again, you better go faster than that, right? Did I drive the same 47 miles per hour the whole way on Highway 17 over the hill? No way, right? So you see the difference? Anytime along the trip, if you look at your speedometer, say, oh, on Highway 17, I'm going 55 miles per hour. That's your instantaneous speed at that moment. But the average speed, you get it now, over the whole trip, take the whole distance, divide it by the whole time, and that is the average speed of your trip. Okay, moving on to the other side of the paper. Velocity. What's your velocity? What's your speed? A lot of people say, they're asking me the same question. And when you're not in physics class, yeah, velocity and speed are probably considered synonyms. They mean the same thing to, in our everyday language. But in physics class, yes, there is a difference, and it's a big difference. If I say, what's your speed, all I'm asking for is how fast are you going. I don't care about the direction that you're heading in. But if I say, what's your velocity, now I'm asking you for 2 pieces of information. Not only do I want to know your speed, but I want to know the direction of your speed. So 60 miles per hour to the north, or 10 meters per second at 30 degrees, or 2 meters per second downward. Okay, so if we're talking about one-dimensional motion, it's easy, because there's only 2 directions you can go, left or right, if we're talking about horizontal motion. If we're talking about vertical linear motion, up or down. If you're on a number line, you can either go in the positive direction or in the negative direction. That's it. So with one-dimensional motion, direction can be implicated with a word like like up or down, left or right, or with a plus or minus sign. But once we get into 2-dimensional motion, I'm just going to introduce that here because I know our chapter's on 1-dimensional motion first. But when we get into 2-dimensional motion, now I can move anywhere in a plane, right? 2 dimensions is a plane. My XY coordinate system is 2-dimensional. And if we, just like in math class, if you say the positive x-axis is 0 degrees and we measure counterclockwise, then this is 90 degrees and 180 degrees and 270 degrees, all the way around to 360 degrees. Now I can describe, if I'm driving my car in that direction, I can describe it with this angle, okay? So that's the middle one there, 10 meters per second at 30 degrees. That's how we would do that. But that's later. For now, we're just going to be moving left or right, or up and down, or plus and minus, okay? One-dimensional motion. Okay, so that's the difference. We call that a vector. Velocity is a vector. Vectors have both magnitude, which is their size, and direction. So if I'm talking about a velocity vector, the magnitude is the speed. If I'm talking about a force vector, how hard am I pushing that, and in which direction am I pushing it? There's another example of a vector. So velocity is a vector. It has speed and direction, whereas speed, I don't give any information about the direction. I just say I'm driving at some speed or moving at some speed. Okay, so since velocity has two parts to it, speed and direction, if I have constant velocity, if I say I'm moving at constant velocity, not only does that mean I'm moving at the same speed all the time, but it also means I'm going in a straight line because my direction is not changing either. Okay, so both things have to stay the same in order for velocity to be called constant velocity, both the speed and the direction. That means if I get in my car in a big parking lot and I push on the gas pedal and I look at my speedometer and it says 20 miles per hour the whole time, but I'm driving in a circle, I am not moving at constant velocity. I'm moving at constant speed, yes, but I'm not moving at constant velocity. Okay? And that leads us into our last little topic here, acceleration. Just like speed is the rate at which my position changes, acceleration is the rate at which my velocity changes. Okay? So let's say you're in your car and you're waiting at the red light, at the metering light on the on-ramp to the highway. Right? The light is red, you're waiting for your turn, the light turns green, and you push on the gas pedal. What's another word for the gas pedal? The accelerator, right? So you push on the accelerate and you begin to accelerate. Now let's say you've got, I got in my Volkswagen van and I went 0 to 60 miles per hour. And you got in your Porsche 911 Turbo, or even better, your Tesla Model X. You got into your Tesla Model X, and you went from 0 to 60 miles per hour. Woohoo! Both my Volkswagen bus and your Tesla Model X went from 0 to 60 miles per hour. My Volkswagen bus is just as good as your Tesla Model X, isn't it? No. Because what am I leaving out? The time, right? My Volkswagen bus goes 0 to 60 miles per hour in 15 seconds. Your Tesla Model X goes from 0 to 60 miles per hour in 2.2 seconds, right? You push that accelerator on the Tesla Model X and you're like, boom! You're back in your seat and you're, not quite that bad, right? But you feel it. You are accelerating, right? And the Volkswagen bus, you're like, and cars are passing you. You're like, come on, hurry up. We got to get up to speed on the highway, right? So that's the difference. The rate at which your velocity is changing. In both cases, the car is speeding up, but the Tesla speeds up much more quickly. It goes from 0 to 60 over a very short time interval. So its acceleration is high. Whereas the Volkswagen bus, yes, it went 0 to 62 as well, but it took a lot longer. So the rate at which the bus's velocity is changing is a lot less. Yes, it's slower, right? So its acceleration is a lower value. It's not accelerating as much. And how do we calculate acceleration? Well, let's compare to how we calculate speed. Speed was change in position. We use the letter x because even if we're moving up and down, which is usually the y-axis, right? It's just conventional to use the letter x to represent where you're at. That's a very common variable to use. And so we say the change in my position divided by the change in time. Okay, and then acceleration now. You know what, I'm going to change this to velocity. This is the magnitude. We call this the magnitude of the velocity. And then the direction is the direction. Okay, and the acceleration is similar. The calculation is similar. Now what we're measuring is how much did my velocity change, right? I went from 0 to 60 miles per hour. There's my change in velocity divided by the amount of time. Again, it's the rate. Delta t equals rate. When we including delta t, gives me the rate at which it is changing. And so if I say I'm accelerating at 5 meters per second every second, So that means so my delta V is 5 meters per second. So that means every second that goes by, my velocity becomes more by 5 meters per second. Okay? So if I made a little table of my velocity values, as time goes on, it would look something like this. 0, 1, 2, 3, 4. 5 seconds go by, and if I start from rest, like I'm sitting in a traffic light, and the light turns green, we say go. The timer starts clicking. Time is moving now. 1 second later, if I'm accelerating at 5 meters per second every second, 1 second later, I'm going to be going 5. Whoops, sorry. I start from rest, so I have 0 meters per second at the beginning. 1 second later, I'm going 5 meters per second. Then a second after that, how fast am I going? 10, sure. And so you see it's pretty simple. Every second that goes by, my speed, or my velocity, increases by 5 meters per second. So my units of acceleration then are meters per second per second. My units of velocity, how do I measure position? I'm at position 5 meters, and later I'm at position 10 meters. So this is meters per second. These are the units. Meters per second, that's what's really happening, but that's a mouthful, and it's difficult to write. So just like in math class, if I was going to simplify that fraction, it would become meters per second squared, because this second here is really in the denominator, right? And meters per seconds times seconds is meters per second squared. So that's my units of acceleration. And if the very first time you looked at it and you saw meters per second squared, you might say, what does that mean? Well, I'm telling you what it means. It means meters per second, because this is how we calculate acceleration. And those are the units of velocity divided by the units of time. Okay? All right, we have one more thing to talk about. I mentioned that this unit, or this chapter, is on one-dimensional motion. So I'm just going to use left and right, okay? So I can either move this way or I can move this way. Those are my only two possibilities. So I'm going to call this way the positive direction, and I'm going to call this way the negative direction. So here I go. I'm walking in the positive direction at a constant speed right now. Then I slow down and I stop. Then I turn around, and then I speed up. And now I get to a certain speed, and I keep walking at the same speed. Now I'm walking in the negative direction, and then I slow down and I stop. Okay? Very simple thing, right? But there's a lot going on there. All right? I'm at rest, and I want to move in the positive direction. Time equals 0. My velocity is 0. Sometime later, now I'm moving at 1 meter per second, let's say. Okay? So my velocity changed, right? And it changed over some time interval. It took me some time to speed up. So I accelerated, didn't I? If we speed up in the positive direction, we say we have positive acceleration. And then when I slow down and stop, you know what, we have to use some numbers. That's going to work better if we use some numbers. Okay. I'm moving in the positive plus minus, okay? So if I'm moving this way, I start here at velocity equals 0, and then I get over here, and my velocity equals 1 meter, 1 meter per second. Okay? So delta V over delta T, the way we calculate that, anytime you say delta, what you're doing is you're taking the second reading and you're subtracting from it the first reading. The final minus the initial is what we call it. Okay? So if I start here and then I take another measurement over here, that was my initial velocity, that's my final velocity. Okay? Okay? So delta V is V final minus V initial. And delta T, of course, in the world we live in, time only goes forward, right? We don't go backwards in time. So time is always a positive number. You can think of it as the final time minus the initial time, but the final time is always a bigger number, right? Because it's later. So a bigger number minus a smaller number is always positive. So delta T is just going to be the amount of time it took to go from the initial velocity to the final velocity. Okay, so let's say I'm at rest, and over a period of 1 second, I get up to 2 meters per second. Let's not make everything 1, because then it won't be obvious. I get up to 2 meters per second. So my final velocity is 2. My initial velocity was 0. So 2 minus 0, and that took 1 second. So now that means my acceleration was 2 meters per second squared. Okay, so I accelerated, and it's positive, right? 2 minus 0 is positive, 1 is positive, so this is positive. So this is speeding up. Okay, now I'm walking across the room at 2 meters per second, and I start to slow down, and I stop. So I went from 2 meters per second to 0 meters per second, and I did that also in 1 second. So when I slow down, V final minus V initial over delta T equals, now at the end I'm stopped. So my velocity is 0, and at the beginning I was moving at 2 meters per second. And again, it took me 1 second. So now my acceleration is negative 2 meters per second squared. Okay? Now I'm over here stopped. And now I start to go this way. And I get going at 2 meters per second. But now I'm moving in the negative direction. Right? And it took 1 second to do that. So to the right, I was moving that way. To the right. Now I'm moving to the left. To the left. And I'm speeding up. My final velocity is negative 2. My initial velocity was 0, right? I started from rest, and I sped up to negative 2. So my final velocity is negative 2. My initial velocity was 0, and I did it over 1 second. So my acceleration now is negative 2 meters per second squared, right? Negative 2 minus 0 is negative 2. Divided by 1 is negative 2. Now I'm moving this way, and I slow down, and I stop. I was moving at negative 2 meters per second. Now I'm at rest. So my final velocity is 0. My initial velocity was negative 2. But don't forget, minus negative 2. Okay? VF minus and V initial is negative 2. And that happens over 1 second. Plus 2 meters per second squared. And this was to the left, slowing down. Okay? So let's try and look for a pattern here. When I move in the positive direction, my velocity is positive. So I'm going to make a little table here. Acceleration result. Okay? When I'm moving in the positive direction and I have positive acceleration, what was I doing? I was speeding up. Okay? So if I'm moving in the positive direction and my acceleration is positive, I'm speeding up. Then I slow down, and when I slow down, my acceleration was negative, but even though I'm slowing down, I'm still moving in the positive direction, aren't I? So my velocity is still positive, my acceleration is negative, I'm slowing down. Then I start to go the other way. Now my velocity is in the negative direction, But when I'm speeding up, my acceleration we saw was also negative. So acceleration is negative, speeding up. And then when I slowed down, I'm still moving in the negative direction, but my acceleration was positive. There we go. So do you see a general rule there? When the velocity and the acceleration have the same sign, I'm speeding up. And when the velocity and the acceleration have the opposite sign, I'm slowing down. So this is why I took so much time to explain this. If I say I have a negative acceleration, a lot of people think, oh, you're slowing down if you have a negative acceleration. But if you're moving in the negative direction already and you have negative acceleration, that means you're going to go faster in the negative direction. You see that? So that's why we try and avoid the word deceleration. Because you say, I accelerate, I go faster. I decelerate, I slow down. Yes, in our everyday talk, that's because whichever way we're moving, it goes without saying that we're moving in the positive direction, because that's the way we're going. So that's the positive direction. And if I slow down, my acceleration is in the negative direction. I decelerated. But we have to be careful in physics class, because in physics class, we could be moving in the negative direction. And then if we decelerate, it depends on if you consider deceleration to be slowing down, then that means you have positive acceleration when you decelerate. So you can see it can get touchy there, right? So I just try and avoid the word deceleration altogether and stick with plus or minus acceleration or speeding up or slowing down. Then there's no question about what's happening actually. Okay? All right. Hang on to those notes. There are going to be some homework problems to try, but I'm not going to assign them today because I want you to focus on preparing for the quiz on Wednesday. And then Wednesday, we'll learn a little bit more about motion, and I'll assign you some problems, and we have some worksheets to help you digest these concepts and help you to learn them. And we'll get going on that after our quiz on Wednesday, which I told you will not take the whole period. It'll be short. All right. Thank you for your attention. Hang out, relax. Happy Friday. And that's it for today.